Well, good morning, everyone, and welcome to our last installment of Precision University 2021, Sprayer Technology to Improve Field Performance. I'm Amanda Doritas, Extension Educator in Champaign County, and I'm your moderator today. And today's speaker is Dr. Joe Luck. He joined the Department of Biological Systems Engineering at the University of Nebraska-Lincoln in April 2012, and he currently serves as the Associate Professor and Extension Specialist for Precision Agriculture. His responsibilities include developing extension and research programs regarding the application of precision agriculture technologies in crop production, as well as teaching in this focus area. His current research and extension efforts are focused on demonstrating agricultural data management strategies and technology applications for improving crop production efficiency. He works closely with interdisciplinary teams to evaluate technologies, including crop canopy sensors for nitrogen application, advanced pesticide application systems, and multi-hybrid planters. Joe was raised on a family farm in Western Kentucky that produced corn and soybeans and operated a small cattle operation. And if you attended Precision University in 2019, you may recall Dr. Luck in his nitrogen sensor presentation. So we're excited to have him back.
Thanks, Amanda. Well, really appreciate the introduction and the opportunity to come back and visit with you folks. Spray application, and I'm probably gonna dip a little bit talking about liquid nitrogen application too. Obviously the two systems that control that are very much related. But spray application, I think it doesn't get quite the attention a lot of times that it needs to. I mean, for most people, it's the most frequent decision what you have to make during the year. As you all have pointed out, it's extremely time critical. You have to be ready. You have all these barriers, weather that, soil conditions that get in the way. So this is, I think this is an area that we really have to focus on. And from the engineering side, we've got a lot of great partners. We saw some of those people in the promotional material there. And it's nice, and I know you all have some great folks in weed science, but the formulations and the proper products and things like that for weed control are probably the most critical aspect. We get to play with a lot of the fun technologies and do technology development. So we'll get right into it. And I just want to recognize a graduate student that works with me, Sam Marks. Actually worked for Capstan Ag Systems for 4 years before coming back to graduate school. He contributed significantly to this. So I thought we would just talk for a second about what it takes to make a good spray application. And as a couple of people mentioned, the mixing, the batching, that's critical. I won't get too much into that today, although I would just hit on it slightly. But we think about three critical things that make a good application: is the rate that we apply, the pattern of the system that we're using, and then the droplet sizes that we generate when we're out in the field. And so we're going to go into a little bit more depth on each of these, but you can just see there a couple of factors that affect those three really critical elements of a good spray application. And the question is, how do you do that as fast as possible? It's always difficult to, as we try and get over the field faster, sometimes our systems are at odds with one another. So just quickly on the batching and mixing, there's a lot to this process. The order that products are mixed together, the different products that are counteractive or antagonistic to one another, things like that. Boom clean out is probably one of the biggest things that we've seen over time that really hinders people. You have these strainers that are continually getting plugged. If you cut a hose or something, or pull the cap off the end of a boom section here like this, you got material in here, and you just imagine a lot of these particles are settling out, and one of the big factors here is the velocity of the particles. So as we're feeding a boom line with 6 or 8 nozzles on it, that material is moving pretty fast at first, But as we get down to that last nozzle, you know, the velocity in that part of the boom is much slower. So these particles start to settle out. And then the big problem is then maybe we switch to a new nozzle package, or, you know, to go to a higher flow situation, all of a sudden that velocity picks back up. And then all this stuff starts to mix back into our product. And that's just I think that's stated a lot of times when people see streaking and product damage. A lot of times that's just material that's getting kicked back up in the boom. So, you know, there's a lot of great technologies out there, pre-batch systems. I saw Surefire's image up earlier. You know, they make those type of systems that help you batch this. You know, there's, I think DuPont had a pre-batch system out there where you could get a bag and add it in. That was metered out appropriately. Surely direct injection systems in the future are going to help with this as we're looking at liquid products. But anyway, I don't want to get too far into the weeds on that as far as field operations, but we all know how critical these are, and we really can't ignore them. So one of the things I would just get you to think about, and I don't know how much time folks spend reviewing, but how do you know how effective you were with your spray application? You know, do you go out in each field and do some scouting post-application? You know, are you reviewing as applied data to verify what happened in the field? And the biggest barrier I see there is a lot of the information we get is really not that great. So this, you know, these are some examples of as applied data that we've downloaded after applications. And you know, what we're seeing is, you know, indication of high application, low application, or okay, and we don't really even know what that means. If you look at this image on the right here, this is from AgLeader's SMS technology, their software. That, you know, we've got these as applied maps that are generated, and you can actually see the overlap here when you reduce the transparency. So this is our coverage polygons as we move through the field. And what we would expect to see here, if our target rate was about 10 gallons an acre, we would really expect to see this entire strip right here in dark green, shouldn't we? You know, it should sum up those data layers and show us that we actually double applied that area. So most of the as applied data that we bring in and generate do not have that option. And that's a shame, and it's something that we're, you know, continuing to try and work on. To promote further data analysis for that. I'm going to spend a couple minutes here talking about things that affect our application. So this is some data you may have seen before. Actually, your own Dr. Fulton helped collect this data back when I was at the University of Kentucky, which has been over a decade ago. But we see, you know, three really critical things, and some of these can be avoided and some of them can't. But you know, we have limitations on all of our rate control systems. That's just the way it is. You know, we can't control everything perfectly when we're doing, you know, boom sections or nozzles actuating on and off, and then we're speeding up and slowing down. One of the most critical things we found in this study was the turning of the sprayer. So let's just look at a couple of these. You know, if you look at this image on the far right, the sprayer is actually making its first pass around this field, going at a pretty steady speed. And then as it starts to slow down to cross this grass waterway, you know, the rate controller is trying to compensate for that, and it really can't do that. So our application rate moves up quite a bit into this area, 10 to 16 gallons per acre. And then you can see in this next pass, same thing as they start to accelerate out of that grass waterway, the rate controller is having trouble generating the rate that it needs to meet that acceleration. So we got low application rate. If we think about turning, you can actually see this is a free fields that we recorded these data on. As we move around these curved paths, you can see the application rate, and this did not have turn compensation. So, you know, our application rate in some of these areas was less than 4 gallons per acre. And we've got all these issues with herbicide weed resistance, and people talk about spray drift contributing to that. But in some of these situations, it's probably more the case that we're just not getting the right dose on. And the problem with turning is, if you think about it, the outside of the boom, just because of the fact that it's covering so much area, it's going to tend us toward these lower application rates in general. We'll see some more data on that here in a minute. Here's another interesting one that I think a lot of people don't think about, and it gets back to that issue of how do I push my field efficiency without compromising application effectiveness. And for the longest time, I couldn't quite figure out what was going on. And this is just a nice long straight stretch. You would think that the sprayer could get up to rate very well and stay there, but it was always low. And actually what turned out to be the case was the operator was driving 25 miles per hour through this part of the field. And, just think about what the requirement on that system is. And this is the nozzle package that they were using. So, if I'm shooting for 10 gallons per acre, at 20 PSI, I'm running 10 miles an hour. If I'm going to, hit 10 gallons per acre, at 20 miles an hour, that's 75 PSI. So we couldn't even get the boom up to pressure to make that happen. So it's one of the things that you really have to consider in your experience. We often trade application uniformity for field efficiency. We can't do that. I just wanted to point this out. So this is a larger image of that field, and this was a field from central Kentucky, very irregular fields in those areas. This is a different way of looking at that data. So if you think back to SMS, that software is not even summing up double application, but if we start to take all that into account, we end up with a much different distribution of application rates. So these green bars that you see here, that's the percent of field area that was applied at these different application rates. So if our goal was 10 gallons per acre, this central bar is plus or minus 10%. So about 35% of this large field here was applied within that range. There was this considerable area that was applied much less than that. And again, a lot of that's back to acceleration and turning, because at any time we turn, we're going to cover more field area at a lower rate. A couple of issues on the high side, again, deceleration, areas on the inside of turns, those are going to contribute to these higher rates. And we can actually use data analytics to break that down further. And we can actually look at what was the contribution of turning movements to that total green area. And then what was the rest of it, kind of grouping that into the controller response. So the controller trying to compensate for speed, trying to compensate for boom section changes. And we can split those out and notice that, the turning movements, that's considerable. It's not something we can ignore, but also just the rate controller itself even contributed more to our off rate when you look at these distributions here. So different way of looking at the data that we, until we started working in this area, we really couldn't see before. I already mentioned, boom overlap and how that can affect things. So we're doubling or maybe more our application rate in these situations. Here's some data that we collected, some as applied data. You can see these areas in blue. This was with manual section control. The operator, I think this was an 80-foot boom with 5 control sections. You can see every once in a while the operator would try and switch on a boom section, but more often than not, it was the master switch controlling the whole boom. And all these areas were double applied. And we'll look a little bit more into this data later, but even switching to an auto section control system, you can see that we really cut back with the automatic sections and those overlaps, but we still have the potential for overlap with those sections. And the big thing to think about there is if you take a little time to think about this, is how you configure those sections is very important. So if you had one boom with 8 control sections, for instance, and I split those up evenly, so each section was about 10 feet. In this point row example, the overlap would be 100 square feet. And let's say I take those same 8 sections and say, well, I'm going to do 3 small sections on the wings because I kind of figure that's where my overlap is going to occur most. And then I'm going to use these 2 large sections here in the middle. We just doubled. Every time we go in and out of that point row, we doubled our overlap. So, my advice has always been, if you can get auto steer or light bar or something, use that and then divide your sections up evenly, so as much as you can. And I know that's tough sometimes because of boom plumbing, but this will give you the least amount of overlap. There we go. don't often see data like this, but what affects spray pattern? There's a couple things that we can talk about. One is obviously the height of the boom, and we'll look at a little data on that in just a second. But boom pressure, we know, can impact the pattern uniformity of these systems. And so this is some data from a spray pattern collection system we have in our lab. We can measure every inch of spray pattern, and we usually set up sections of nozzles, so maybe 3 or 5 nozzles. And then we run a lot of tests, looking at different nozzles, pressure, changes in the system. And this is what we saw when we looked at, so this is an air induction nozzle, AIXR 11003. They recommend those being run at a 20-inch height, and that's what we did. If we looked at a 20 PSI pressure setting, and again, this is kind of the center nozzle would be right in between, these this 15 and 16 collection tubes here. So this is one nozzle with the corresponding nozzles on each side. If we drop the pressure down to 20 PSI, look what happens to our actual pattern. And so you could think about this as flow rate across that, underneath that set of nozzles. These blue bars here indicate our ideal flow rate. So if I were to take, the flow of that nozzle and divide it up into 20 inches in terms of the width and just kind of superimpose that across there, this is what I would want ideally, and this is what we get. So right beneath those nozzles for that pressure setting, we get half rate of what we wanted to apply. In between those nozzles, so this is going to be sort of in between that next tip and the one we're at, we're getting a lot more flow out of those. In this case over here, almost 50% more flow in those areas. So that's something we don't often see, as a potential cause for application error. But, again, back to that field earlier, if I'm driving too fast and the boom can't keep up, that could be a problem. We'll talk about some technology solutions here in just a minute, but just another example. This is another set of data that we collected for a couple different boom configurations. So, these are our XR 11003s, 20-inch spacing, 20-inch height. You see that data here. And then a XR 8003, again, 20-inch spacing and 30-inch height is a recommendation. And you can see what we're looking at is we ran these nozzles at different heights above our pattern collection system. And over here, we measured the CV, or the variation. So, what is spray pattern CV? Well, it's a measurement of the distribution. So just thinking back to this, this would be a perfect distribution here. So this could be a pretty much 0% CV if I had perfect distribution. The coefficient of variation of the pattern in red here is actually close to 20%. So it's a terrible CV value. And from a practical standpoint, if I could get a 5% CV calculation from my boom, so if I could go out and pattern that entire boom, that would be ideal. 5 to 10%, well, we would usually say somewhere beneath 15% would be acceptable. But once you get beyond, 15%, this is what you're looking at, and this is just not gonna work. So what we did was we ran these boom configurations at different heights. So for the orange data set, our ideal height was 20 inches, and that's pretty close. The manufacturer data would suggest that. You can even see that even as we increase the height above the pattern system, we'll start to increase our CV, which is not good. And of course, as we decrease it and those nozzles get closer to the target, we're not getting the ideal distribution. We're going to increase those CVs as well. If you look at the 8003, it's the same thing. It turned out they were a little bit more resistant to error. So we, ideally we'd be around this 30-inch height. We could actually drop that a little bit and didn't have considerable difference. But as we started moving, further lower to the pattern or up higher from the pattern system, we started getting those increases in CVs that we don't want to see. And so that's just trying to kind of make the case we'll talk about here a little bit, boom section height, boom height control for those types of issues. Spray drift. It's probably the biggest issue that we have today. It's the one thing that the EPA really has gotten into and tried to provide guidance on. So we know this is not going to be a problem. As we move, as urban and suburban areas continue to expand, if you think about that, the bigger those areas get and start impacting agricultural areas, that impact area it increases more and more each time we see that expansion. So impact to suburban and urban areas is just going to increase over time just because of that growth footprint. And then, as we've had, dicamba issues, I don't know how the issues have been there in Ohio, but it's huge out here. And a lot of that's because of the continuous wind that we have. But picking the nozzle selection is just critical here. If you're looking at contacts, having the right pressure setting with the right tip is just critical, because pressure on ground systems, as we increase pressure, our droplet size decreases. And so, that's where you see this chart over here, just an example of, what the deposition for the smallest particles could be in just a 3-mile-an-hour wind. Those could go hundreds of feet. If we think about temperature inversions, that this is examples of where, they've done studies and found drift traveling miles, because it hits that inversion and it just kind of keeps going. So a couple of really critical issues. And again, two of the biggest things was, in speaking of that, one of the things, and I'd like to give Sam credit for this, he kind of went out and started looking at what are some tools that are available to help with, wind speed monitoring. There's the old way to detect an inversion was to build a fire and see if, if you hit that layer and you could see the smoke kind of traveling along the inversion. There's actually some tools out there now that that you can use, a handheld option for weather, inversion potential. There's online tools now that give you an idea. And I know IBM, working with, the Weather Channel, those type of things, are looking at online tools to detect, and predict when we're going to have inversions. So there's a lot of tools that are going to come available to help us monitor weather and help us, identify potential, issues with inversions and weather and climate issues. So those are some things you could look into. Really, automatic boom section control, and we've been talking about this, and I would be surprised if adoption is very low at this point. But this is one of the technologies that we've seen that just has tremendous opportunity for payback. And there's a couple of things to think about. So the shape and size of your field plays a critical role in how much payback you're going to have. And then we talked about a little bit the boom size and how you distribute those sections can also impact how much, reduction and over application. And here's just an example of that from the studies that we did back, I referenced when John was working with us at Kentucky. Here's 4 sprayers, and this was actually a common sprayer before and after automatic section control was added. But you just look at the over application as in those fields. So when this operator on a 3,000 acre farm had a manual 5-section boom, they over applied 14.5%. So you think about that, over 100 acres field, they sprayed 114.5 acres. Just the addition of auto section control with a couple of extra sections at the end of the boom greatly reduced that overlap. You continue to increase sections, you can continue to see how that overlap is going to be reduced. So this system here, this was basically 2 nozzle. Every other nozzle was being controlled and actuated, and those folks got down to 2.3% in some of the worst fields that I've seen in terms of boundaries and obstacles. But if you're curious, and I would be glad to visit and help you out with this if you ever need it or curious. But one of the things we found was we could quantify the irregularity of a field by looking at the perimeter of that field and then dividing it by the area. So think about a fairly nice square field, like the 40-acre field you see here on the left, one grassed waterway in there. If we add all that area up, including that waterway, and divide it by add that perimeter up, including the waterway, and divide it by the area, we get a value probably somewhere around this, 100 feet per acre. If you look at a field like the one you see up here in the top right, it's a 10-acre field. And if you if you sum up the perimeter of that and divide it by the area, you end up with something larger, like in this 600, feet per acre range. And this is the error. So this is the over application versus those values we collected on all these fields. And so this top trend line you see here is this manual 5-section system. This is the system that averaged 14.5% error across the entire farm. Notice that the actual error ranged anywhere from 2, 3, 4, 5%, all the way up to 40%. So this little field that we see here was the field that these 2 points right here. It was sprayed twice, a 10-acre field, that sprayed, 13, 14 acres. So it's a huge amount of overlap. You can actually start tracing these down. So these boxes we see here, this trend line, that's the addition of automatic section control that averaged about 5.7%. That's the reduction from that point to that point, and from this point all the way up to this point for those fields that had such high overlap. So still a lot of overlap, even with auto section control, but just look at the reduction. We went from 40% overlap down to less than 10% in that one field. And then as you add sections and look at these different operations, again, you can see, even with individual nozzle control, we can probably still guess we're going to have maybe 1%, depending on the field, 2% overlap. But those high resolution control on boom sections could potentially really save. And then again, it depends a lot on what the fields look like that you're operating in. So this is a field from that study. So we actually saw this field, if you recall, in the earlier maps that I showed you, that had the telephone poles going through the field. We saw the speed changes kind of going in and out of this grass waterway. This is that 100-foot boom with about every other nozzle or 2 nozzles grouped together. And this was back before, personally, before I had a smartphone with a camera on it. So this was back in 2009, probably. So I had to think ahead and bring a digital camera. Not that people use those anymore, probably, but this is actually a picture of the sprayer as it's traveling down into this corner of the field. You can actually see the other advantage of these auto section control systems is, you can map these waterways, these sensitive areas, and the systems will shut off as they pass in and out of that. So you can see that, probably 1/3 of that boom is turned off, 1/3 of that boom is still on as that sprayer is traveling down into this area. And, I don't know if Dr. Fulton recalls, he was down in that area of the field when we were working with the system, but he certainly wasn't a hindrance that day. It was nice to have him out there with us. So what are some of the other solutions? So auto section control, again, it's a great option. I think if you don't have it, it's likely going to save some time and money. But some of the other systems that are out there, we talk about these pulse width modulation or PWM nozzle control. And essentially, what those are these individual nozzle bodies get their own solenoid valve. So these checks that we had on the nozzle bodies to keep those systems from dripping, basically that gets pulled off. We screw these solenoid valves on here. You can see this is from the capstan system on the right. And basically we're pulsing those on and off at different frequencies. And that helps us with rate control on these systems. We'll look at a little data from that in just a second. But another potential benefit here is not only can we control the rate of flow through those systems, and you can see that here, we can control the pressure. So the pressure is controlled on the boom system side. And then as the duty cycle of those is pulsed. So you can kind of see that here. For whatever frequency we're operating at, we can pulse those nozzles on, 20% of the time. Obviously, they can be all off or all on. But as we increase that duty cycle, what we're doing is we're increasing the flow through that nozzle. And typically, the pressure is going to be pretty consistent. So one of the things that helps with is, if we think about that, we can kind of maintain the pressure. And so through that, we're trying to maintain our droplet spectra. So not relying completely on boom pressure for that. There's some products out there. These are the systems that I know of today from T-Jet to Deere to Raven and Capstan that offer these kind of systems. Another benefit of these is that flow rate turn down ratio. So again, if you think about typical nozzles, we have to increase the pressure 4 times to double the flow rate. Well, with these systems, because we have the pressure control and then we have the duty cycle control of that nozzle, kind of this linear relationship, we can actually get up to 8-to-1 in some cases turn down ratio for those systems. So it's a great opportunity to extend the low and high flows that you might see in the field. It can really help compensate for those speed changes. And if you have the right nozzle selected for that application, it can help you, with your spray drift issues as well by kind of maintaining that boom pressure and just using the valves to control the flow rate. Here's an example. So I said I would flip a little bit between spray and liquid nitrogen, but here's a data set we collected. We've been doing in-season liquid nitrogen application for probably about 6 years. This is the first couple of years of that project. We actually ran kind of a typical fixed orifice system with liquid stream nozzles. And then after the first year, we switched over to one of the Capstan PWM systems. And what we found was if we were looking at the flow rate from that compared to our target rate, and so that would be, perfect would be 0% error. If we look at that plus or minus 10%, again, the PWM system kept us within that range 54% of the time, compared to 28% of the time with the standard, just pressure-based fixed orifice system. So is it perfect? No, no technology is going to be perfect, but that's a significant improvement. And again, thinking about these variable rate systems where, which, spray application is not quite really there, but again, just think about that in terms of speed changes. If you have to speed up and slow down, these systems can really do a good job of help keeping you closer to your rate. A couple of other options that I would just throw out there, and I'm not sure if anybody's looked into these, but variable flow orifice nozzles. So these variable flow nozzles, there's an internal mechanism here, or in this case of the Delavan system, it's actually the orifice itself and a little pre-orifice inside. But basically, as you increase the pressure, the orifice increases. So that quadrupling of the pressure to get a double increase in flow rates, that's not really the story here. These systems can really extend that, and the data would suggest maybe a 4-to-1 or 8-to-1 increase in flow rates, in turn down ratio across a typical set of pressures we might see. One of the nice things is, particularly with these Delavan systems, is they can continue that spray pattern maintenance. So when that pressure drops, that in that system, the orifice closes a bit and it helps maintain spray pattern. Again, droplet specter can be maintained a little bit in these situations because we're not relying so much on pressure. So if we really speed up, we're not relying solely on pressure, to match that flow rate. The orifice can open some and help out. So is it a perfect solution? No, but it can help there. And certainly with, with some of the systems, like we mentioned Deere before with their ExactEmerge, but their new system that allows you to change nozzles kind of automatically, if you're switching products is a time saver as well. We talked a little bit about the impact of boom height on spray application. So it's something that we have not been able to collect a lot of data on, but we know that obviously if the boom goes up, there's farther distance to travel. There's going to be a more opportunity for those particles to drift. We know that as the systems get too close to the canopy, we're not getting the distribution of material. And then if you have terraces or something like that in your field, digging the end of the boom into the ground and destroying nozzle bodies and nozzles, that's not much fun either. So these are just a couple of systems out there that can help with that. Again, it depends a lot on your fields you're operating in. If you're lucky and you have perfectly flat fields, probably not a huge issue there, but certainly in eastern Nebraska, we have folks that are looking at that technology because there are still a lot of terraces out there that cause uneven application. Most people are I think Autosteerance and auto-steering guidance is probably one of the top adoptions. So nothing much here except for really something interesting and new is the trend toward machine vision for spraying systems. So Raven has a system like this. I think several of the big companies are coming out with systems where they're using machine vision and stereo vision here to actually detect the rows. So, and certainly there's mechanical feelers that can go down the rows. So if you're, spraying in corn and you want to reduce the damage there. But those kind of systems could really save time and allow people to travel a little bit faster in the field when they're spraying and certainly not damage as much crop. So I think some of those technologies are worth taking a look at. And, it's like buying a car, add-ons cost a lot more, but, as we see more people increasing their, new purchases, things like that, sometimes those costs of a little bit extra tech are well, certainly with as expensive as sprayers have gotten, it's like throwing a lawn chair off the Titanic or something like that. But anyway, it's something that, it's kind of think about maybe next time as you do an upgrade, there might be some of these technologies that could be a small cost, but maybe give you some good payback in terms of field efficiency. These technologies, so weed sensing technology, some of these are fairly available commercially. I'm not sure if you've seen much on the weed seeker system, but that's basically an integrated nozzle control with greenness sensor here. So it's using reflectance to see if there's anything green to spray. I'm not sure what the ruling is on that with emerged crop, but in terms of burn down, these have been systems that can pay back by just spraying what needs to be sprayed. Really large fields down in Australia, I think that's been one of the primary adopters, not so much yet in the United States, but it's an opportunity that's out there. We're starting to see more again of machine vision, image analysis on the go. So everybody's probably familiar by now with John Deere buying out Blue River technology, but basically with cameras mounted, and we're going to see this transition to row crop sprayers. We've talked to a couple of companies that are hoping to launch some of this technology in 2022. But being able to, use video cameras to identify plants that should be there and then the weeds that should not be there on the go. And with these PWM systems in particular, just pulsing that on to hit those weeds and not spray, a broadcast. That's where that technology is headed. So we will see that, in the near future in terms of row crop production. So I hope I'm doing fairly well on time and give people time to ask questions or have a little discussion if you want to. But just a quick summary of some of the technology out there that I think is worth looking into. If you haven't already looked at boom section control, it's probably the top technology to help save money. Again, think about what you have. There's potential based on your fields. If you've got maybe very few automatic control sections, maybe going as you upgrade to a sprayer with much higher resolution could pay back still. So it depends a lot on how many acres you're covering. Turn compensation, if you can't help it and you have to make turns, it's worth taking a look at. So are those places where you're, on the inside of turns, is it causing a lot of crop damage? On the outside of turns, are you not seeing the weed control that you need? If you can't help it, that could be a technology that you might want to take a look at from these PWM systems that are out there. Again, they will help with your rate control response. They could reduce your overlap down to single nozzle level, which could be another potential benefit. And then, of course, like we mentioned, they can help mitigate some of the drift issues that we see. Boom height control, again, I don't see a lot of adoption there, but we may find here before too long that that's going to be a really great way to help mitigate spray drift and then also improve our uniformity across our target area. So and again, I'll throw that plug out there as we think about variable rate approaches, and probably not quite so much in the spray business yet, but certainly in the liquid application in general. These variable flow or variable orifice nozzles, pulse width modulation, things that can affect field efficiency. In the first year when we ran those, the standard, straight stream nozzles with pressure control on the boom, we were seeing speeds, application speeds down to 4 miles per hour because we had to hit these high nitrogen application rates. In some cases, driving 16, 18 miles an hour, just because we couldn't get enough pressure in the boom for low application rates to open the check valve. So these systems, if you think about it, anytime we were driving less than 8 or 10 miles an hour, we were just wasting time out in the field, and we cannot do that these days with the time, as everyone mentioned, and with working days. It seems like getting reduced every year because of poor weather. It's something we really have to focus on. And then just again throwing that out there, the weed detection technology is coming. Some of the preliminary data that the companies, this needs really to be verified, but some are suggesting 75% reduction in chemicals compared to full broadcast. So I think there's a lot of opportunities there with those systems. We just need to get them out there and do some evaluations. So that's I think some exciting opportunities, and with the future of fully autonomous field robots, there's going to be opportunity to really take advantage of some of these things that could be coming within the next 10 years. So I really appreciate the chance to visit, and there's my contact information. If you want to reach out, get information on any of this stuff, I'm always glad to visit.
All right. Well, thank you, Joe, again, and thank you for all the information. I'm just going to run through a little bit, a couple more slides here. We might be done with Precision U, but we're not done with our presentations yet. So if you guys are looking for more information, join us next month with AgTech Tuesdays. You can see the topics we have planned there, go.osu.edu/AgTechTuesdays to register. And then upcoming agronomy team programs, you can find all of these again at agcrops.osu.edu, but a couple of upcoming ones this Thursday, and then February 4th, we'll be talking about seed production. Here's where you can find eFields online if you don't want to send in for a printed copy. go.osu.edu/eFields. And then just one more thank you to our sponsors for making this program possible.
Sentinel, the industry-leading liquid row monitor from Surefire Ag, eliminates costly mistakes that could subtract revenue from your bottom line. Sentinel utilizes your existing in-cab display to provide instant notification of flow variances and row blockages. Sentinel is the smart choice that pays for itself. Quick Draw drives sprayer productivity. Surefire Ag's automated spray tender system can meter, mix, and load a 1,000-gallon batch in just 8 minutes. Less time loading means more acres sprayed. Quick Draw from Surefire Ag, driving sprayer productivity. Learn more at surefireag.com.